Good morning, everyone. Wherever you are in the world, I hope you and your loved ones are healthy and safe. My name is Randy Bell, and I am the director of the Global Energy Center at the Atlantic Council. Thank you for joining us today for EnergySource Innovation Stream, where we highlight new energy technologies with the potential to reshape the global energy system. Today, we will be hearing from Bob Mumgaard, Chief Executive Officer of Commonwealth Fusion Systems, who will discuss how CFS aims to bring fusion energy to market through its compact fusion project called SPARC. Before we get started, 2 administrative details. First, you can follow us on Twitter at AC Global Energy and use the hashtag InnovationStream. Second, after Bob's presentation, you can submit questions through the Q&A function on Zoom, and I will try to get to as many of these as I can. If you're watching on another platform like YouTube, unfortunately, we cannot take your questions. So please let me welcome Bob Mumgaard to the Atlantic Council. Bob, thank you so much for joining us today.
Great to be here.
So Bob, how are you and Commonwealth doing during COVID? How has that impacted your timeline and your work?
Yeah, so now 6 months in, right? It's the new normal. The first start of it, we're a very hardware-centric company, so we had to really refactor what we were doing. We went and got more space. I think we're one of the few people that went and got more real estate during COVID. But got more space, spread people out, moved some operations around, and then fortunately, our team was already pretty adept at remote work, so that transitioned pretty well, and since then we've actually doubled in size since the beginning of COVID. So there's a whole part of the team that this is their experience with Commonwealth Fusion Systems.
You have anyone on your team who you've actually never met because you only see them through Zoom?
Yeah. Oh yeah, several actually.
Yeah, we hired on my team somebody who I haven't met, and the joke is we have no idea how tall she is.
Oh yeah. I met someone recently. Yeah, I met someone recently, and I didn't recognize him because I had no view of the context of them in the real world.
Yeah. Well, looking forward to learning more about Commonwealth. Why don't you share your screen, and we'll get started with the presentation, and then we'll do Q&A afterwards.
Great. So I'm very excited to be here to talk about fusion energy and CFS. And I think for a lot of people, you might have heard of fusion energy in the movies or Marvel comic books, things like that. But one of the big advantages of fusion is that it's basically the power source that powers all the stars. So it is the power source of the universe. It's the power source in the sun. And it does that by taking the lightest elements and combining them together to make heavier ones. If you were to do this on Earth, it could be really disruptive. So here's an example of how it works. So inside the sun or inside a commercial fusion system, you take 2 isotopes, variations of hydrogen, which is everywhere. You combine them together and you get helium out of this. And in the process, you make a lot of energy. How much energy? It's about 200 million times more energy than if you say burned fossil fuels per pound of input. So it's in a completely different realm, which is why people were so confused about how old the universe was and how the stars still worked. Is because they're very, very energy efficient in this process. It's the most energy efficient process in the entire universe. If you were to put that on Earth, it would be very, very disruptive. And I think this is a good example of how disruptive this would be. So here you have, an oil tanker, the basis of our modern energy economy for the last 100 years. If you just took the seawater that this is displacing and you filtered it, and then you fused it the way the sun does, you would replace all of the oil in that tanker, and you would not emit any CO2. And when I say, the water it displaces, I actually mean only 50 gallons of the water it displaces. So it's a completely different magnitude of energy. And in this process, you basically have an energy source that has effectively no fuel, or fuel that's equally distributed everywhere. You have no meltdown, no long-lived nuclear waste, no uranium, no plutonium. You can build this as a machine that goes somewhere, runs. You can build it basically anywhere in the world. It makes a lot of power on a small plot of land, like a gas turbine. And it's very, very scalable. You can manufacture it. So this is like civilization scale energy. And it's not just Commonwealth Fusion System that has been looking at this. In fact, the scientific community has been looking at this for a long time and has been steadily increasing our understanding of how to do this. And in fact, the largest construction project in Europe today is a fusion machine in the south of France called ITER. And here's an example of that machine. So inside the machine, you have a super hot plasma, basically the stuff inside stars. It fuses, makes heat you take out and you run a process with. The challenge is that this machine is very large. Here's a person. And this is a very big, expensive project. So it's unclear how this scales to commercial energy, but it is clear that scientifically this is doable and that it's potentially transformative. Otherwise, you wouldn't do this type of project. And if you take, the progress that we've done in the world scientific community, including the machine ITER and all the governments and basic research that's led to it, and you look at how close we are to making a fusion machine that can make more power than it takes to run, it's often surprising to people that we're actually pretty close. This is a plot, scientific plot. I'm an MIT PhD, so I apologize, but I have to have a graph. And if you look at this plot, up here is the realm where you make fusion machines that make more power than they take to run, which of course is what you need to be commercial. And all these are data points of other machines that have been built. And you see they're actually getting pretty close to making more power than they take to run. And it's taken us a couple decades to do this, but this is 13 orders of magnitude. And while we were doing it, we were actually going faster than Moore's law. So that's the basic state of the play. We're sitting there right below, this break-even point of, generating excess energy that you can then harness to drive a commercial process. The big government programs have focused on one particular technology, the one that's the highest performing. It's a technology called a tokamak. It's basically a donut of plasma. But now we're also seeing the emergence of other private companies like CFS, but there's now 20-some odd of these companies with over $2 billion of private capital invested. That's actually more money than in, say, all of small modular nuclear reactors. And they're looking at a whole variety of concepts because we're seeing that this is doable. Maybe there's multiple ways to make it work. These concepts, span a very large range of risks in terms of science, engineering, market risks. But it's very encouraging to see everything from Lockheed Martin to startups attempt to do this space. And it's really setting up a landscape of fusion energy commercialization, fusion energy science that hadn't been there before. We like to think of it in a quadrant graph like this, where you have, two trade-offs. You have a trade-off on how confident you are that the system can work. Basically, what's your scientific basis? Have you seen things like this before? Do you have simulations? And also, what is it that you have to build? How big? How expensive? What does this thing look like? And up in this quadrant, we have the government programs who are incrementally increasing the science, but at very large scale. And down here, you have some startups. And what's really interesting is that CFS, we're a concept that we believe lives up here. And the reason that is because you're seeing these other technologies that are unrelated to energy, unrelated to fusion, be applied to these types of problems. In our particular case, it's a breakthrough technology of a very, very strong superconducting magnet. And magnets, what does that have to do with anything? Well, it turns out if you want to bottle a star on Earth, one of the ways to do it is to make a magnetic bottle. And if you make that magnetic bottle with very, very strong magnetic fields, you can make it smaller and smaller and smaller, basically more and more compressive, more and more insulating. And you can get to the point where you can take that giant machine and shrink it. And this has been enabled by a revolution in material science in superconductivity that came out of labs thinking about transformers and power lines. But if you build a very, very strong magnet, the strongest magnet in the world, which is what we're doing right now, it means that you could drastically shrink the scale of the most scientifically advanced fusion concepts. So this is what it looks like. You could take the large international $50 billion project, and you could take all that same science and same physics, and you could put it into a package that's 50 times smaller with this new transformative magnet. And that's this machine we call SPARC. And so that's what Commonwealth Fusion Systems in partnership with MIT, which is where we came from, or a spin out from MIT. That's what we're working on. And what we think that could do is put a new option on the table for fusion energy, which leads to new options for energy at a pace that's much, much faster than what, say people thought 5 years ago. And that's combining the scale and flexibility of a startup, building things that are, scale of what you build if you were SpaceX, or not SpaceX today, but SpaceX maybe 10 years ago, or, small privately funded nimble endeavors, but with the science of the big government programs. And this is not just a theoretical thing. This is what CFS is actually out there doing today. So we're about 100 people full-time in the company, about $200 million of investment from Breakthrough Energy Ventures, which is Bill Gates and Bezos and others backed. And then from 2 super major oil and gas companies, Eni, the Italians, and Equinor, the Norwegians. And then additionally, a variety of early investors and things like SpaceX. And what we're trying to do is build that magnet as fast as we can. And we are about just starting the construction of the final magnet. And we expect to demonstrate it next summer. And then we'll move on to building SPARC, which will be the first machine in the world to make more power than it takes to run. That would be about 50 to 150 megawatts of heat. And this is a render of that machine. And in fact, just yesterday, we published a special issue in a plasma physics journal that showed all the plasma physics that I just talked about is consistent and is consensus, that if you have this magnet, you could build this machine and this machine would work. And we think we can build this machine by 2025. And that's what we're actively trying to do. And we think we'll start construction on this next summer. So it's a very exciting time for Commonwealth fusion systems. It's a very exciting time for fusion overall. And it's starting to see, what would a 2030s fusion machine, a commercial fusion machine in the 2030s, look like in the energy landscape? And ask that question and understand, the lay of that ecosystem if that were to happen. And that's very exciting. Great.
Fantastic. That is really, really exciting. I have tons of questions. If the audience has any, please be sure to put them in the Q&A. But since you ended on the talk about the investors, what is it about the oil majors, particularly the Europeans in particular, but even American oil majors are investing in fusion? Not your. I know Chevron just made an investment, not in your company, but another one. But what is it that's why are they looking to fusion as opposed to other technologies?
Yeah, well, I think we're seeing the oil and gas sector, really try to make the transition to what does the future of energy look like and become energy companies. And so as part of that, a portfolio makes sense. And fusion fits a very interesting part of that portfolio, because basically what fusion is can you build machines and run projects that once you figure out how to make this work from an IP and scientific standpoint, it becomes a lot more like building a turbine than it is like building a solar cell, or it becomes a lot more like running a project like an oil refinery in terms of pulling things together. It's smaller than an oil refinery, but pulling a plant together that makes a lot of energy in a small space. Than it does like building a wind farm offshore. And so that fits a certain skill set and a certain organization of energy if you want to power energy dense things, whether that's cities or industrial processes. And fusion fits that quite well without the emissions and without the nuclear meltdown and proliferation issues.
Right. We have a question from the audience from Andrew Kadak, which he wants to know, what is your Q target?
Yeah, so the SPARC machine is Q greater than 2. No one's ever done greater than 1. And the record right now is 0.7. And this machine that I just talked about is targeting Q greater than 2. However, if you read the papers and the coverage of the papers that came out yesterday, you'll see that it actually has quite a bit of upside in it. It's closer to Q greater than 10. And at that level, when you're making 10 times more power than it takes to run, that is a really serious energy system. That is a system. You push a button, you make a whole bunch of energy basically from nothing, and let the button off, and it stops. And that would be very, very interesting, very transformative for the energy sector.
So the way you describe it, where you're just pushing a button and turning it on and off, that does sound like load following. Is that possible in this system? Can you follow the load, or do you just sort of have to create base load and hard to modulate the amount of power it's generating?
Yeah, so this system's fusion in general is very different than, say, nuclear power. In fact, it's the exact opposite. It's
Right.
atoms and
Yeah.
and one of the big advantages there is that it's actively fueled. It's actively controlled. You turn it on, you turn it off, you turn it up, you turn it down. It doesn't have any memory about what happened before, which means you can make these things, ramp them up and ramp them down. And that's what we do in experiments. I mean, we change these things all the time because we're playing around with them. And so the question about load falling simply becomes an economic capital efficiency question, not a technical question. It's simply like you've got a fixed asset there. How often do you want to run it? It's relatively low O&M, almost zero fuel, and so mostly capital. So this would fit a regime of a low marginal cost, higher capital cost, dispatchable zero emission heat source. And that is not a market product. That's not a market that has a product in it today.
Right. That is remarkable. In terms of, once you get the first prototype, the first one built, how long do you think until you can commercialize it? And is it, should we think about the production of these more like manufacturing? So you're just building them in a factory one after another, or are they really construction projects that are site specific?
Yeah. So, the machine SPARC, that's the one we're building next. And we're actively finishing the siting for that. So where we'll build that. And we hope to announce that before the end of the year. That one, that's not a commercial system. That's still something that we're proving out our technology, proving out our team, our supply chains, things like that on. The commercial systems, we think, then follow as soon as possible after that. So in the early 2030s is the hope. And so this is not something you're going to see, suddenly on the market in the next 3-4 years. This is still further out than that. But it's also not something that you should wait for half a century for. Once they're there, these machines are pretty much like building one way to think of it is like they're a bit complicated, but they're not so massive that you have to go out and build them in the field. So it's kind of like turbines, airplanes, manufactured products, large offshore wind turbines, those types of scale of things, where you can get learning of multiples. These are made out of basically metal. It's, there's not that much crazy material in this. It's really like, can you, forge metal? Can you put it together the right way? Which means the delivery model could be something that's much closer to, say, like how GE delivers, an F7 combined cycle turbine, right? Instead of a delivery model, we have to go out into the field and stick build it. That's not what you want to do. You want to build something that you can make replicable and you can deploy at a large scale. And that's the goal.
Yeah, fascinating. We have a question from an anonymous attendee asking about what government policies are needed to help accelerate this process, but also to make sure that they are deployable. Is there a regulatory environment that's needed? How does that work, the relationship with the government?
That's a really, really great question and a great thing in this particular forum to talk about. So the fusion, obviously, we do not have a fusion industry today, so we have to make one. And part of that is, what is the role of government in incentivizing and creating the playing field, and also in regulatory. And that's an active area of discussion. Actually, just this week and next week, there's several activities going on in DC. So last week, they passed a comprehensive energy bill out of the House. And as part of that, fusion was in that bill for the first time, as we need a national policy on fusion where we do things like cost shares to get the industry up off the ground in the same way we did for like commercial space. Research and development, bolstering that in the pipeline, and also creating the regulatory and export structures that match the technology. That was all in that bill. So that's now in the House and waiting Senate. That's very exciting because the government has supported fusion actually quite well over a long period of time. It's in the category right now, though, where it sits next to the people that make new elements and the people that discover the history of the Higgs boson. And so that's not a great spot to develop an energy technology, but we're seeing it transition into things like RPE and into applied programs. And that's what this bill is aimed to do, help that transition. Additionally, on the regulatory side, fusion is not nuclear fission. It is not a nuclear reactor. In fact, it doesn't, according to the NRC, it doesn't meet the regulations as a nuclear reactor. It actually meets the regulations as like a particle accelerator in a hospital. And so there's enough framework to get going based on that. And next week, they'll have a forum at the NRC, a public forum, where they're going to discuss the future of fusion regulation and how we build an innovation ecosystem where we figure out what these technologies are, because it's not just CFS, it's other players and different architectures. And the hope is it will get a flexible, fast-paced, innovation-focused regulatory structure that meets the hazards that fusion actually poses. And so these are open areas of discussion in the government, not just in the U.S., but it's a very competitive landscape. China has a very big fusion program, Japan, Korea, the Europeans, and so it's a emerging field.
That goes very well into a question from our friend Doug Hengel, who asked if there are any foreign startups in fusion and Chinese companies in particular, he asked. So what does that landscape look like?
Yeah, so I mentioned there's 20-ish fusion companies. There's four sort of big ones. CFS is one of them. One of them is in the UK, one of them is in Canada, and then two of them in the United States. And so that's the four biggest ones, and there's a bunch of mid-tiers and smaller. And new ones come all the time. It's actually seen some really great growth. There are some European ones, startups. There are a few Chinese now. There's one particular Chinese oil and gas company that is private as such, they say, and that is putting in significant resources into fusion, in addition to the Chinese government, which is part of their larger energy 5-year plan, is participating in ITER along with the US and EU and everything like that, but also building a parallel program, a quite aggressive parallel program to develop domestic technology.
Fascinating. So, one of the things that we focus on a lot at the Atlantic Council is the geopolitics of energy. Oil and gas has a geopolitical angle. Nuclear fission has a geopolitical angle. What are the potential geopolitics of fusion? Are there minerals or metals that are in limited supply that would go into a fusion system or whatnot? What do we have to think about when we're thinking about those types of geopolitical questions, or even just competition among countries for developing technology?
Yeah, it's a really, really great question. And I think fusion breaks some of the traditional ways to think about energy and geopolitics, because the mass flows are so small. The largest mass flow that humanity does today is carbon and oil, and this has none of that in it. And then additionally, you don't have any of the mass flow of uranium. You don't have any discussion of who has it and what are they doing with it. You can swear off uranium if you have a fusion system, because you won't need to run a domestic energy nuclear system if you had fusion. So that changes the game quite a bit. There's not really specialized materials in this. In terms of raw materials, there's definitely technology in this that is, whether you have access to, say, thin film deposition to make the superconductors, or advanced manufacturing to manufacture the metal parts, sintering, things like that. There's those types of technologies, but at the end of the day, this is not really about who controls the atoms. It's really about who controls the knowledge. And to move energy into that sphere, that will be very different than the sphere we're in now, because a power system like this solves a lot of the sort of elbow room problems that come with energy. If you have this, why do you need a pipeline to go to a neighbor you might not like? If you have this, why do you need the long-term relationships for shipping things in? There's those types of pieces that, in a world where everyone wants to sort of control their own destiny, fusion could fit.
So it's an intellectual property issue more than sort of the geopolitical chessboard that we think about when we think about oil and gas or whatnot.
Yeah, that's one way that's the way we see it. And it's interesting too, because in the intellectual property space, fusion comes out of the, Atoms for Peace, and it was declassified all the way in the 50s, and it's been part of detente. It has been a cornerstone of the international scientific exchange. It is open. You could go online and read all of our SPARC design, open access, published, peer-reviewed, built on, bookshelves and bookshelves and bookshelves of published research around the world. And that's been a real boon to, I'd say, humanity, but also allows us to do things like build companies like CFS. Mm-hmm. And so it's riding on top of the larger open science ideas, and the triumph of that model, I would say. And now we're starting to see, okay, like turn that into something that's practical. And it'll be interesting to see how that plays out. We hope it stays, in an open world where, playing fields are relatively level, and we see who comes up with technologies at the lowest price point and most attractive market fit.
Yeah, I mean, this is fascinating. And maybe I'm getting ahead of things here, but how are you thinking about technology transfer? If you look at where energy demand growth will be, it is predominantly over the next set of decades in the developing world. And there are real concerns about making sure the developing world gets access to power, it gets access to energy, gets access to cheap energy. How do you think about making this technology getting to India, to sub-Saharan Africa, et cetera?
Yeah, I think the key thing here is to keep it open. As a company, we want to be in those markets. And in order to do that, we need sensible export control laws. And actually fusion, because of its history, is in the open on export controls. Let's keep that, right? Because if we can develop these technologies, we can bring these to the world in a way that brings benefits back to the U.S. And to the technology developers and people that invested in the science, but also provide the world access to a clean energy solution, and that fits into all sorts of climate goals and social justice goals, and clean pollution cleanup goals. You could use this to repower coal, if a coal power plant, when it comes available.
Right. Okay, I want to take one more question that sort of ties the technology to the geopolitics. And it's from an anonymous attendee who asks, why don't you have uranium or plutonium to power your system, like many designs require enriched lithium or tritium? Those plus other elements can lead to weapons and can lead to proliferation. How does that fit in with your geopolitical answer? And how are fusion companies in general approaching the topic?
Yeah, so it's a good question. So the comes to like, what's the social license for the materials that are in any system? So in fusion, there is no uranium or plutonium because you're on the other end of the scale. So instead you're using hydrogen, deuterium, and lithium. And hydrogen, deuterium, lithium, those are all available. You have an intermediary that's called tritium, but you don't have very much of it, and it's something that you generate on site, and you don't even have to start with it. You can actually self-generate it. And so that means you can literally start up one of these plants with material that you can buy in a chemical supply book in terms of the fuel, which is very different than enrichment of uranium, plutonium, or things like that. And so from a fuel standpoint, it's going to be very, very difficult to box that, right? Which we think is a really good thing. Which means instead you're in a market creation mode of how you get this technology out.
Bob, thank you so much. We are out of time, unfortunately. I think we could have this conversation for another for half the day if we wanted, but I know we're all busy. So thank you for joining us, and thank you everybody out there for tuning in again this week. Be sure to connect with Bob on LinkedIn and follow CFS. Hope you all join us for the next episode of Innovation Stream on October 7th at 10:30 a.m. Eastern, featuring Trude Sunset, CEO of Gas Nova, who will discuss Norwegian Longship CCS, an industrial-sized project for carbon capture and storage. We also hope that you will join us for another event this week called Securing the Energy Transition, Innovative Cyber Solutions for Grid Resiliency. That's on October 1st at 9:30 a.m. You can register for both of these events on the Atlantic Council website. Thank you to everyone who helped put this event together, including Laura Macedo, Roger Morales, Jackson Styron, Emma Smith, and Olga Kokova. This presentation will be available on the Atlantic Council website, YouTube, Facebook, and Twitter. So please do share it with your colleagues if you think they will be interested. Really appreciate, Bob, your time today. This is really remarkable. So I'm looking forward to following the technology as it progresses. So maybe we can get you back on as you're starting to build SPARC next year. And we'll see all of you out in Zoom land next week. Thank you so much.
Thanks for having me.